And we are live. Yes, my name is Sasha. I'm brand manager at YozmaTalk, and this webinar is brought to you by YozmaTalk. And I wanted to know, maybe for now, where you're joining from, if you can type that in the chat, and how can you scale from 1 to 10 your experience with system design? You system design something from zero. While we're waiting, let me introduce our today's speakers. So we've got Pata here with us today. And here's a senior engineer with a lot of experience, and he's a really pleasure to talk to. In the middle of this webinar, we'll have a short pause, and I will tell you a bit more about 10x Dev. This is a closed community that we are creating right now, and I'm gonna invite you to it. So stay put, and don't forget to write your questions in the chat. At the end, we will have Q&A session, and also we have here an opportunity to join with your voice. So if you'd like to add something at the end or ask your question using your voice, you can also send a request and join us here, like a part of our podcast. And without further ado, then I'm just gonna give the mic to Pata. Okay, hi.
Hello, everyone. So today I want to talk about system design in a practical way. It is mostly system design fundamentals, because for main system design and to go in depth to system design, we will need not 1 hour. There is such a big courses for each section of system design, how to do system design, and etc. So today we are going to speak only about fundamentals and have some examples from live example and from technical side. So let me share the presentation. Okay. So basically the system design can sound very abstract at first. Architecture, components like databases, caches, load balancers, queues, replicas. But the ideas are not only about software. We can see that the same ideas are in real life. So today I will start with a simple example, a restaurant during rush hour. A restaurant has customers, orders, kitchen, cooks, carriers or waiters, waiting time, some failures and peak traffic. So basically, these are almost the same problems that software systems can have. After that, we will translate the same concepts that I will talk about into some TikTok platform or Instagram platform, like it will be video platform example. It is a good example because it has a heavy rates, heavy media delivery, like video uploads, recommendations, caching, queues, and many failure scenarios. The goal of this talk is not to design the perfect or any system. The goal is to understand the thinking process and how we start from requirements, estimate, scale, choose components, and make trade-offs. Main thing that I want to mention, the system design is not only drawing boxes on a diagram. Drawing boxes is the visible part, but the real work is making decisions and trade-offs. When we design a system, we define the architecture, first of all, how the components are organized. We define the data, what we store, where we store it, and how it moves. So, for example, a system that must respond in 100 milliseconds will be designed differently from a system where a response is in 10 seconds is acceptable. So a system that must survive a data center failure will be designed differently from a small internal admin tool. So let's start with our example. Imagine that we have a restaurant at 8 p.m. It's a rush hour, as we know. Customers are coming in. Some are ordering online. Some are sitting at tables, and some are waiting for delivery. At the beginning, maybe the restaurant has one host, it means one kitchen, one cook, and one courier or one waiter. When traffic is low, everything works fine. A customer places an order, the kitchen prepares the food, and the food is served. But when more customers arrive, problems start to appear in that time. The waiting line becomes longer, this is similar to high latency in software development. The customer does not care how complex the kitchen is in the restaurant. They only care how long they wait. And too many orders mean the restaurant needs higher throughput. Throughput is how many orders the restaurant can process per minute or per hour, like any parameter we can set. If the kitchen can only process, for example, 20 orders per hour, but 100 orders arrive, the system becomes overloaded. Now imagine, for example, one oven of the kitchen breaks. If the whole restaurant depends on that one oven, this is a single point of failure in this case. So because of this, one broken component can stop the whole system. To improve the system, we can add more cooks, for example. That is horizontal scaling. The naming of this in system design is horizontal scaling. We can open a second kitchen, for example, that gives us redundancy and replicas. We can prepare common ingredients and before peak time. That is similar to pre-processing or caching something in software. And the host can decide which kitchen should handle each order. That is similar to load balancers that we will have. So, as I mentioned, we need to have scalable system, but we have a different type of scaling. So the first scaling option is vertical scaling. In the restaurant example, I will say this means improving the same kitchen, buying a better oven, like using better tools, organizing the workspace better, or asking the same team to work faster, for example, or longer. In software, vertical scaling means using a bigger server. For more, we will have more CPU, we can have more RAM, or we can have faster disk or better network. This can help, but it has a limits. Any vertical scaling has a limits. At some point, one bigger machine or one bigger kitchen is not enough. In that case, we have the second option. The second option is horizontal scaling. So in the restaurant example, we can add more cooks, we can add more cooking stations. In software, we can add more servers or more replicas instead of one component doing all the work. Many components share the work. Then we have replicas. So, for example, in restaurant, a second kitchen is a replica, and the first kitchen is the main, and the second kitchen is the replica one. If one kitchen has a problem, the other kitchen can continue serving customers in software, read replicas or service replicas, help with scalability and availability in this case. Next one is load balancing. The host or order desk should not send every order to the same kitchen, as we know. The host should check which kitchen has free capacity and route the order there. In software, this is load balancer. The load balancer sends traffic to more healthy application instances. For example, we can have many instances in our application, and load balancer can decide to which instance to give this request to process it. Also, we need the queues. If the kitchen, for example, is busy in restaurant, we do not lose the orders. We keep them in sequence, process them safely. In software, queues like, for example, Kafka or RabbitMQ, as we know, absorb bursts and let workers process jobs at a safe speed. And the final one is, as we know, everyone, cache or pre-processing. A restaurant can prepare common ingredients before peak time. For example, they can cut some vegetables till the order, pre-process some kind of foods before getting orders. In software, we cache common data or pre-compute expensive results. So requests are faster when users arrive. For example, we can have some jobs that will process some calculations and save the data in the cache, and we can get the data when we need. So this is pre-processed, and we can get the data when we need from the cache fast. So here I want to talk about latency and throughput in example of restaurant to be more understandable. So the latency is the total time from the customer's action to the final visible results. In one online, for example, restaurant system, it could be time from clicking order to receiving confirmation. So for delivery, it could be the time from ordering to receiving the food. The throughput is a different thing. Throughput is how many orders or updates the restaurant can process per minute. A restaurant may have good latency for one customer, but bad throughput when many customers arrive at the same time. There is also like when jitter or some unpredictability. When one customer waits 2 minutes, another waits 20 minutes. This feels unfair and unreliable. In software, users also dislike unpredictable performance. That is why we often care about latency, not only average latency. Average latency can hide bad user experiences if the average is, for example, 5 milliseconds, but 5% of users wait 10 seconds. That is still a serious problem. A good design tries to keep latency predictable. This is about this. And the next is also coming the real our technical side platform example. So I choose TikTok, or we can be Instagram, where we have more. It is interesting, I think, in this perspective. So I want to show how we can design similar platform like TikTok or Instagram, and what is the best way to do architecture here. So basically, system design can sound very abstract at first, as we have architecture components, as I said, databases. This part, I want to design a video platform. Before choosing databases or servers, we start with requirements. The main functional requirements are users can upload videos, users can watch an infinite personalized feed, users can like, comment, and follow. The system can recommend videos, the system can send notifications, and the system can moderate content for spam, unsafe content, or copyrighted material. For video upload, we do not only store the file. We usually need to validate it, store the raw video, transcode it into different formats and resolutions, generate thumbnails, and run some moderation checks, and finally publish the video. For watching the feed, latency is extremely important because users expect the next video to appear instantly. And if the app feels slow, users leave very quickly. And me too, and everyone, I think. So social interactions are also high volume, and likes, comments, follows, and shares can happen many times per second. Some of these must be stored strongly, while counts can often be eventually consistent. The recommendation service is central for example, TikTok-like video platform. It chooses the next best videos for each user. This service may use user behavior, video metadata, social graph data, and ranking models. So at a high level, we have mobile clients, an API gateway, backend services, storage, some content delivery network, databases, cache, queues, and workers. The next part. So from system design perspective, the important part is that we need to make capacity estimates before starting designing the system. Capacity estimation helps us avoid guessing. We do not avoid guessing in any case. So we do not want to say randomly that we need 10 servers or 100 servers or certain database. We need raw numbers to drive architecture decisions. Let's assume that we have 50 million daily active users. Let's also assume that each user watches 100 videos per day, and that gives us 1 billion video views per day. Also, to calculate the average read traffic, we divide 5 billion views by 8,000, 86,400 sorry, 86,400 seconds in a day, because a day has 86,400 seconds. And that gives us around 58,000 video views per second on average. But traffic is not perfectly flat during the day. There are peaks. If, for example, we use time more peak factor, the peak risk can be around 290,000 videos per views per second. So now let's estimate the uploads. So we suppose that 1% of daily active users upload videos. So that means that we have 50, 100,000 uploads per day. Like dividing it again by 1,400 gives around 6 uploads per second average. So at first, 6 uploads per second does not sound huge, but video upload processing is heavy. It's very heavy process, and each upload can require storage, transcoding, thumbnail generation, moderation, metadata creation, and etc. For storage, if the average uploaded video is 20 megabytes, then 1,000 videos per day means around 10 terabyte per day of raw video, and before replicas and before transcoded versions. This is that count. In reality, storage can be much larger because we may store several versions of each video. The key insight here is that the video bytes should not go to the application servers on every view. Video bytes should be served from object storage and content delivery network (CDN). Metadata feeds, likes, comments, and user relationships go through databases and services. So let's show some diagram of this system design based on these capacity estimates that we did. And here we separate the system into different parts and responsibilities. This is important because the traffic, media delivery, and background processing have very different requirements. For example, mobile and web clients send requests to the API gateway, and the gateway handles common concerns like authentication, rate limiting, routing, and request validation. Behind the gateway, we have services. So behind the gateway, the upload service handles video uploads. The feed service returns the video IDs and metadata for the user's feed. And the interaction service handles likes, comments, shares, and follows. The user service handles user profiles and relationships. The recommendation service chooses which videos should appear next. For heavy asynchronous work, we use a message queue like Kafka, for example, or it can be SQS. When a video is uploaded, we do not make the user wait until everything is fully processed, and we enqueue jobs for transcoding. Also, workers consume those jobs, so we can scale workers independently. If uploads increase, we add more workers, like without changing the feed service. So the next is the metadata database, which is stored users, videos, comments, relationships, and video metadata. At scale, this database may need sharding and read replicas. In this case, also helps us Redis cache for faster reads and sessions. Also, we have object storage. This is the object storage for videos. This is for storing the actual video files. The CDN serves content delivery network, serves video bytes from edge locations close to users. And this is a critical because application servers should not stream every video directly. Upload path. This is the upload path that this should be asynchronous by design because the user should not wait for heavy processing of it to finish before getting a response. For example, in step 1, the user sends upload request. The API validates authentication and file size, file type, and maybe basic rules. In step 2, the raw video is stored in the object storage. So this is important because once the original file is safely stored, we can retry processing jobs if something is fail. Step 3 is when we create queue jobs. These jobs may include transcoding the video into different resolutions, generating thumbnails, like checking content safety, detecting copyright issues, and extracting the metadata, of course. Step 4, workers and process. In step 4, multiple worker replicas can consume jobs from the queue. If uploads spike, we add more workers in that process. And the final step is when processing succeeds, we publish the metadata and the video becomes visible in the app. Why async? Lower latency, user gets quick response, received. Retries, failed processing can retry without losing the file and scales independently, adding more workers when uploads spike. Okay, so sorry, I need to go for 5 minutes break and we will continue from here.
Well, thank you, Pato. Answering on the question in the chat, yes, you have the slides, and also I'll send everyone who registered to this webinar recording early next week, also with a short follow-up and with a presentation attached. So I want to ask you whether you heard about 10x Dev as an idea. Can you type in the chat if you've heard about it before, just a plus? Okay, C minus. I like that because it's great because I can tell you something interesting, something new. A few minuses. Okay. Okay, I'm glad because it means that this information can be beneficial to you. So there is an idea in engineers community and AI first communities right now that a lot of noise was created by artificial intelligence and a lot of noise regarding whether people will keep their jobs in the future, whether AI will replace them or not. And here in YozmaTalk, we believe that it's not going to replace them, that it will change everything that we see about these jobs right now, but maybe in a better way. So the idea is if, for example, 10 years ago to finish one project, there were needed a team of 10 engineers. Right now, in a few years, it could be one engineer who knows how to work with artificial intelligence, with agents, knows how to build system, how to design system design. And here in YozmaTalk, we believe in that idea and we want to be a part of it. That's why we are right now developing a closed community for engineers who want to scale and who want to grow. I'm going to show you also a few examples. Like the market has already shifted, and you can see it right now in your current jobs. You can see it in the social medias, and we can see it inside the company as we are talking with a lot of people and a lot of clients. And usually, when we talk with the clients, we have one persistent point and one ask. Client ask us if the person had previous experience with AI engineering, AI prompting, AI agents, because AI change output. And also the hiring has shifted. If you open jobs right now in engineering platforms, you can see that almost every startup proposition that has it includes AI vision, AI efficiency, and also capability. This is the new currency. The new currency in the future, because clients don't ask us how much people we can provide. They ask us how much this person can do using AI. And the problem that a lot of engineers are not adapting fast enough just because there is no place to it. Like we use AI develops really fast and much faster than you can follow it. It's natural because new AI model features itself almost every week. For example, we can see the few tendencies of Claude with the new AI models last month and this month as well. So you just do not adapt fast enough, and we use AI tools superficially. So this is basic prompting or basic question asking, but not the whole system, because usually we don't have time to teach AI how to help us. And it means that basically we are AI users and not AI first engineers. And the idea of community is to create people and to make them AI first engineers. And right now, there's no place for that. Of course, we've got LinkedIn communities, Telegram, Reddit, etc. But this is mostly noise because there's no place to show how you work with AI. For example, if you've developed some feature, you can share it with others. the same as you can join some meeting from other colleagues to see what they are really using in their work. No peer feedback. You are not getting feedback from your colleagues, from the teams, from other teams in your company, just because there's no culture like that. And of course, no evaluation based on your output. And as I've mentioned, what we have right now on the internet, that's mostly communities with a lot of noise. No gate means no signal. This is foreign programs. For example, Israel Tech Gym won't localize in Ukraine. So what 10x Dev is, this is practice over content, closed over open, peer over teacher. But I see that you're back. Just I need a few more minutes and I'll give the mic to you. So for whom is 10x Dev, you'll ask, and what's in it for you? So if you can create more, you will cost more. So you can earn more. You can secure your future because as I showed you in the chart, that if that's okay right now, in a few years, AI first engineering AI capability will be like number one in every job description. And also an opportunity to go to better projects because there's a sea, an ocean of startups that's starting to work the way you can work. Who is it for? This is for senior engineers who have something to share and who want to see what others are doing right now, for middle engineers who also want to grow fast, and engineers who build in public, who want to have a place, a space to show what they're building. And in the community, we will have four roles like members, the people who are joining boot camps, joining quizzes, joining challenges, etc. Curators, that's the people who create those challenges or help with the creation of bootcamp and mentoring others if they have something to show. Ambassadors, that's me. And guests, this is throughout our network, invited CTOs, VP&D of startups and progressive communities. And right now we are planning to have our first bootcamp at September. It will be online. It will be curated with our curators and will be led with lecturers who are invited from our network as well. The value exchange, you give like approximately 4 hours a month for attending those webinars, challenges, live coding sessions, etc. But what you get in response, that's much more because you can be the voice of a new generation engineers. And I'm going to send the link to register and to apply to 10x Dev here in the chat. And also it will be included in follow-up after this meeting with meeting recording. And if you have any additional questions, don't hesitate to ask me something. If you have an idea you want to share with others, but you don't know how to do that, you can also write to me. Well, and I would really love to see your applications. I'm going to stop sharing right now. And yeah, I'm still here in the chat and I'll get back to you at the end. But for now, I'm giving the mic back to Peta. Just one more thing that I want to say, that don't forget to write comments in the comments or questions if you have one.
Okay, we stayed in upload part. We talked about it, I think, and the next part, important part of system design, is the fifth path currently of the video platform design. So the fifth path must feel instant, and when a user opens the app, they expect, as I said, the first video and the next videos to load almost immediately. The feed service first checks whether we already have a pre-computed or cached feed for the user. If Redis has a uh, load feed result, we can return video IDs very quickly. If there is a cache miss some, the feed service asks to the recommendation service, as we see here, and to generate or refresh the feed instantly, and then the result can be cached again for future requests. So for metadata, the system can read from database replicas that we have. Read replicas reduce the load on the primary database and improve availability. The actual video bytes should served by the CDN video bytes. So by the CDN edge and not to the servers or app servers. This means the user gets the video from a location close to them, and our backend only returns the metadata. URLs and feed decisions also our backend returns. This separation is very important because the app servers handle control, flow, and metadata. Object storage and CDN, content delivery network, handle the heavy media bytes. Cache and pre-computation keep the feed faster, and replicas reduce the database pressure by having more replicas. So in this case, cache hit return pre-computed video IDs, cache miss ask recommendation service, then cache result content delivery network. Video content is served from edge locations, not app servers, and read replicas reduce the database load and improve availability. Next is about replicas, failover, and consistency. Replicas helps us scale reads, but they introduce an important design choice. These usually writes go to the primary database, but reads can go to the replicas. And this lets us handle more read traffic and protects the primary database from overload. If the primary database fails, we may promote a replica. This is failover. For example, multi replicas, if we have, help us survive zone failure. Backups help us recover from bad deploying, for example, for accidental any deletion or data corruption. But replicas can also lag behind the primary. That means a user may write something, and for a short time, the replica may not show it yet. For some data, this is acceptable. For example, view counts, likes counts, analytics, and some feed updates can often be eventually consistent. If a like count updates a few seconds later, users usually accept it. For other data, we need stronger consistency. Payments, for example, wallet balance, order state, security settings, and important account actions should not be eventually consistent in the same way. So the architecture depends on the data. As I said, not every part of the system needs the same consistency model. Good system design means choosing the right consistency level for each feature. So, handling spikes. How we will handle the spikes? Of course, using load balancers and queues. For example, a video platform like TikTok can have sudden spikes, and celebrity posts a video, a trend starts, a notification is sent, or a live event creates a burst of traffic. The first protection layer of this is the API gateway rate limit. The rate limiting protects the system from abuse bots, accidental client bugs, and of course, extreme spikes. Then the load balancer, of course. As I said, spreads requests across healthy API replicas, and if one replica is unhealthy, for example, the load balancer should stop sending traffic to it. For synchronous requests, we scale API replicas horizontally, but not all work should be synchronous. Heavy work should go through queues, and a queue absorbs bursts. Instead of forcing workers to process everything immediately, the queues keeps jobs safely and workers process them at controlled speed. For example, if we upload processing, notifications, analytics, video transcoding, and moderations are good candidates for asynchronous queues. This protects system, the user facing like API stays responsive while background workers catch up as capacity allows. For example, if queue lag becomes too high, that is a signal to add more workers here and or reduce work per job. So the next one is about observability. Know before users complain. Like system design does not end when we draw the architecture, and in production some kind of things will be failed anyway, and services may be slowed down, queues grow, the database replica lags we will have, or we can have content delivery network providers can have some problems, for example, or sometimes we can do bad deploy. And that is why observability is essential. It closes the feedback loop, like logs, uh, answer the question, what happened? The logs should include errors, logs should include the request IDs, user actions, and important context. Without good logging, debugging production issues becomes guesswork like. And about metrics. Metrics answer the how much and how fast we process some requests. For example, we track requests per second, latency, CPU and memory, queue size, error rate, cache hit rate, replica lag, and more. And because of these metrics, we can calculate everything this. And if we need more CPU, we can add. If we to improve our latency, if we need something else, for example, we need to add disk memory and etc. Tracing it is something that if we have something slow or very it is in database, it is in gateway, it is in cache. A request may go from gateway to feed service, then to Redis, then to recommendation service, then to the database. This distribution tracing helps us see which step is slow. And of course, the alerts, we can set up alerts in any case. For example, I have an experience to set up in alerts when, for example, we will have replica lag more than 50 seconds, for example. And in this case, everyone will receive a email or some alert that we have replica lag and we need to fix something. So we do not want alerts for every small issue, but we do want alerts for very serious conditions. So the good observability as a result here lets us know before users complain anything. It also helps us understand which part of the system breaks first in the system and traffic grows. And the final takeaways, and this is the same ideas apply from restaurants to this video platform. In the restaurant example, helps us understand the institution. This video platform, like TikTok architecture, shows us how the same ideas appear in real software systems. First one, that we need to start with requirements, understand both functional requirements and non-functional requirements. What should the system do in this case? Second, the most important thing in system design is the estimation of capacity. Without this, we can't calculate the traffic, we can't buy correct storage, we can't have correct memory, we can't know read volume based on this, we can't know write volume and peak traffic. These rough numbers are better than random guesses. The third one is the design of for latency. In this case, the most of cases we need to use cache, CDN, replicas, pre-computation, pre-calculation, and good data placement to make the user experience faster as we can. The fourth one, design for failure. We need to use replicas, failover, queues, retries, backups, and assumed components will fail in this case. The fifth one is to have separate responsibilities. This is the microservice architecture logic idea. So we need to have separated business logics in separate microservices to have separate responsibilities. So services should have a clear ownership and clear APIs. Heavy work should often be asynchronous. The sixth one is that we need to measure everything like logs, metrics, tracing, alerts, and services should have clear ownership and clear APIs. Heavy work should often be asynchronous. And in the last, I will say a simple question I like to keep in mind like this. What breaks first when traffic becomes 10 times bigger? If we can answer this question, we are already thinking like system design. So that's it about my presentation. And I want to show also the system design that I made for example, for TikTok. As you can see, as I said during presentation, what we have here, we have as first the different microservices that have each responsibilities like check feeds, upload the photo, and download the photo. These are three separated microservices, but it is related to one API gateway. And by this API gateway, it's the request is going to load balancer. Before this, if we have some prepared queues, first of all, the mobile client is going to call from direct SQS or Kafka and keep in touch during this request. From API gateway, it's going to load balancer, and load balancer, in this case, I have read and write, of course, replicas. He decides where to go to request. If it need to write, it go to the right database. If it need to read, it goes the appropriate replica read server. Then the write server, if it goes to write server, it goes to user service. And for example, some data here is cached in the Redis when we create. Some data is go to write to database, and after that, if some data is need to be cached, it's cached in the Redis. Here also it can be write server directly update database and retrieve the data from here. If there is some, it is coming from uploading photo service, the write server is going to upload the photo in S3 bucket. And after uploading the photo in S3 bucket, we need to save the photos or videos in a CloudFront in content delivery network CDN, and this is the best way to caching this data, the photos and videos. Then what about here? We will have, this is the metadata part. So from database, this is worker. So pre-processed job that the feed generation service is going to feed generation service from database. And here, as I said, is preparing some data workers in Kafka. If we need to do something by getting from worker or queue, it will get to do in mobile client. The feed generation data is doing like adding likes by using again microservice. Like service we will have follow service that someone is following. We will have comment service that will add the comment in feed generation service, and it will save again in the database. And of course, here also we have some get add posts when we get or adding some posts, and again it will pass from worker, and by post service this will be separate microservice, save it in the metadata database. So that's it. If you have any questions, I would like to answer.
Wow, thank you. Thank you. Even for me, when I'm not a technical person, it was really insightful. But as I posted on LinkedIn, when we've got a dry run, I already knew that it will be incredibly insightful session. And right, if you had any questions, please don't hesitate to write them down in the chat, because we have Peter here right now and he can answer it. So I'm just gonna take a time for a few more minutes to say your questions, or if you're leaving already, you can also type in the chat to say Peter, thank you for this incredible presentation.
Thank you everyone to participating and listening.
As I mentioned, I'll be sending a follow-up next week. And if you have any questions, you can also write to me, to my email, and we can keep in touch. So yeah, thank you very much. I see that a lot of people are saying things also in the comments. By the way, if here's someone present from YozmaTalk, don't hesitate to send cookies for for Peter for this presentation. And again, thank you. Thank you lots, and see you and have a nice weekend.
This weekend.
Bye.
Bye. Bye.